Okay, so this is our problem. A cube-shaped steel sculpture has side length of 30 meters. So it's a pretty big sculpture. How heavy in kilograms is the sculpture if the material's density is 9.1 grams per milliliter? So let's remind ourselves how we do a calculation question like this, the dimensional analysis question. So I'll give you a moment to sort of think about it, jot down some ideas and so forth. And like I was saying previously, it's good to be organized. What was given to us in terms of numbers with units from the question? What do we desire from this question? So in this case, we were given that the side length is 30 meters. We were given that the density is 9.1 grams per milliliter. We desire the mass of the object in kilograms. So remember that with enough practice, these kinds of questions, you start to get an intuition for what to do, but that requires practice, and that's what we're doing right now. One thing that we can always sort of rely on is the dimensional analysis, looking at the units and seeing where do they fit together. So remember, that means looking at each unit and asking, what does it measure? So grams, I see, measures mass. Milliliters measures volume. Kilograms is a mass. And meters, well, that's a length. So I noticed that sort of 2 out of the 3 match each other, right? I have mass with mass, so perhaps those 2 go together. The problem is the other numbers I need to use is, or other units, volume and length. So we have to do a little bit of thinking for this. How do these sort of connect? Is there some outside information that I need to use, or is there information within this problem that I'm gonna sort of compute, I guess? And so we're going to go with the fact that you can turn length into a volume. Calculate the volume. Then they'll match. So we literally have a cube that is 30 meters on each side, meters. So that's exactly what we're going to do. So the volume of a cube is the side length cubed. So what does that come out to? That's going to be 9 times 10 to the, oh no, it's 2.7 times 10. So what is it in proper scientific notation? 2.70 times 10 to the 4. What is the unit? Well, in the calculation, it's meter. I am now raising it to the third power, cubic meters. Now we have the matching units that we need. So I can see my starting number has now volume. I had to actually calculate the volume from the length, but that's part of these kinds of questions, being able to see, well, I want to jump between volumes and masses. So if I were given a dimension, like the dimensions of a cube, I want to think about, well, how can I turn that into a volume? And we have an equation for that. And that's going to be similar to one of the calculations in the experiment. But we have this now. Now we're going to start doing our conversions. So I'll rewrite the number, 2.70 times 10 to the 4 cubic meters. Now I need to convert it using milliliter as my conversion factor. However, we can't cancel unless they match, so we need to get cubic meters into milliliters. So without skipping steps, let's do the whole thing. So how can I easily, or as painless as possible, convert cubic meters to milliliters?
Convert to cubic centimeters?
Yeah, there are a number of ways to do it. I think the easiest way would be to go to cubic centimeters as well. So we're going to do a meter is 100 centimeters. And what do we do to that? We cube it. Yep, thank you. Absolutely. So that's, we can simplify, we can maybe distribute if we want, or if we're careful, we could leave it as is. It's up to us. So I don't know if this feels more comfortable, but let's go ahead and distribute. So I'm gonna put cube, and cube there, and then cross it out because we've now distributed it. That might be the nicer way to go because we can see that we can now cancel cubic and cubic. So we just have to be mindful it's 100 cubed now. Now, this one is the one that I said, please memorize this quickly because it's a nice conversion. Cubic centimeters to milliliters. Why is it so nice? Because they are equivalent. It's 1-to-1. Yep. There we go. Maybe I'll do a highlight for this. But we're going to cancel, 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 cancel. We're now at milliliters. So now this is dimensional analysis. We're looking at the units and how can we get them to cancel. Now I have a number that I'm going to use for my next conversion. It just so happens that this conversion is my density, but that's the beauty about dimensional analysis. Those numbers that we record actually end up being the way that we turn one unit into another. So this is really nice. The only thing we have to be careful of is making sure our numbers go in the right place. So what am I going to do? I'm going to turn this into a fraction. I want milliliters to cancel. So why am I saying be careful? Because the number has to go with the first unit. So since 9.1 goes with the grams, 9.1 grams is on top. And I urge you to do it this way because I find that it makes makes it easier in the sense that there's less error when you perform the calculation this way. So what I mean by that is that never try to do math with a number written like this, with the slash mark. You start to get confused about which part of the fraction is which. So my suggestion is anytime you see a number given like this format with a slash, turn it into a fraction and make sure that you write the number with the first unit. And then you can flip it as is, because that's the number one way we get these kinds of little typo errors, but that'll cancel. We've now reached grams in our calculation. Where do we go from here? We want kilograms. So I'm not done with my calculation. it's going to have one more conversion factor. Because I want to cancel the grams, they have to be top and bottom to cancel. And that means my desired unit has to go on the top. How many grams are in a kilogram? That's 1,000. And these will cancel, giving us our desired unit. So what I've just shown is that you can do this multi-step problem all in one step as long as you chain together the correct conversion factors. So the rest is to put it in the calculator. So we're going to multiply by our first number, and hopefully you can do this with me so you can double check that you're plugging in, and it's looking good. So multiply by 100 cubed, or in other words, 10 to the 6th power. This is fine. Multiply by 9.1. And then the rest is all division. There's only one more number to divide. And what do we get? It's a fairly large number. I'll give you a chance to calculate it yourself. I come up with 2.46 times 10 to the 8th power kilograms. So if we remember how many zeros that number has, that comes out to be, what is that? 246 million kilograms. Pretty heavy. But this metal cube that we have is the size of a building, pretty much. So we would expect that it would be pretty heavy. And that's another thing, take a moment to reflect on your answer and think, does this make sense? And yeah, a 30-meter cube made out of pure metal, that's going to be pretty heavy. But that's the sort of basis of what we're doing in experiment 2. We're using density specifically as a major conversion factor for things. Not only that, but the premise of the experiment is to first calculate the density by taking the mass of the object, divide by the volume of the object, and then any other calculations can utilize the density as a conversion factor. And so that's what we're doing in this experiment. Okay, so with that, I'd like to just leave the rest of this time for office hours. So that means what you can do is on your own, take a look at experiment 2, download the materials, start looking through this, this stuff, and we can get to answering questions during the remainder of the time. Oh, I see. Oh, thank you. There is a typo that I made. Yeah, so this value is 2 sig figs. So my answer should actually be wrong color. 2.5. There we go. Thank you very much. And I'll highlight that. There we go. Awesome. Thank you. So yeah, densities are measurements, so they do have sig figs. Oh, and then I'll go ahead and stop the recording.